Hi! For my problem solving video assignment, I decided to create a problem for my Algebra 1 and Transmath 3 course. And Transmath 3 is basically a pre-algebra intervention course at my school. But as I was reflecting on the reading, and particularly the chapters from Rays, I noticed that most of the assignments or practice that I do with my students in class really fall under the definition of exercises and not problems. And so I created this problem, planning to use it in Algebra 1 and Transmath 3 in the fall for our solving equations unit. So before I read my problem, my group defined a problem as something with an unknown aspect that requires critical thinking and creative thinking in order to solve it. So here is the problem that I made. So this is what I would give to students, and then they would have time to figure it out to practice their solving equation skills. Create 3 multi-step equations using the variable x that meet the following requirements. The final solution of each equation must be x equals 10. Either addition and/or subtraction must be an operation in each equation. Either multiplication and/or division must be an operation in each equation. Solve each equation to show that x equals 10 is the correct solution for each. So again, this is what I would give my students. And it's got that unknown aspect because the 3 equations or 3 equations that they make are unknown, and they have to figure out different ways in order to create this multi-step equation that equals 10. Critical thinking is not only the problem-solving aspect, but just critically looking at the requirements of this problem and making sure that they meet each of them and understand what it's asking. And then the creative aspect is the fact that they need 3, and so they need to be kind of creative to make them look a little bit different each time. Also notice that the requirements are set up to make this at least a 2-step problem because the students need either addition or subtraction and one of multiplication or division, but it doesn't limit them to having it just be a 2-step equation, so it could be. They could get more inventive if they wanted, but it does set up that minimum requirement. Alright, so understanding the problem, the first thing we have to do is just make sure we know what the problem is asking us. And so there are a couple different parts with all of our requirements. So create 3. We need a minimum of 3 different equations when we're done. That's what we're handing, that's our goal here. Multi-step is also a very important part. Multi-step means that we have to have more than one step. So for example, if we had like x plus 2 equals 12, that's just a 1-step equation. So that actually wouldn't work for this. We need to have at least 2 steps, which means we have to have at least 2 operations. And that part kind of goes hand in hand with the second and third requirement, because it requires that we have one of addition or subtraction and one of multiplication or division. So right there it's saying we have to have those 2 operations. Let's see, it also explicitly tells us to use the variable x, so that's where our problem solving comes in with that variable x. As we're doing this, we can't just create any old equation because we need to make sure x equals 10. And then it also specifies that we should solve or basically check our answers when we're done, just to show or prove or justify that our solutions actually work. So our final answer, something that we're looking for, or what the real goal of this situation is to create an equation. So I'm just going to make a random one that might not have 10 as the answer. So something like 2x minus 5 equals 20. It's an equation. It uses x. It has 2 operations because it's got multiplication and subtraction. It uses multiplication from our multiplication or division. It uses subtraction from our addition or subtraction. And then on that last part would be to make sure 10 is the answer. But essentially that's what we're looking for. That's our goal here. So how could we do that? What could we do? So our next step is to devise a plan to figure out what could we do. How could we make this happen? And so the first thing I did was just think about different strategies. So I could maybe work backwards. I could try guessing and checking, just playing around with numbers until I kind of stumble upon something that works to get a feel for how to do this. Maybe I could set up a simpler problem, so start off with something like x minus 1 equals 9. So that's just a one step, but it's simpler and similar to my goal, and so I could expand it into a two-step from there. I could consider equivalent problems, which is kind of like looking at simpler problems. I think thinking out loud helps with all of these, just to make sure, again, you're meeting those requirements and that you're kind of making sense. Thinking out loud just helps to make sure you're doing all those things. Or I could break the problem into parts. So now that I kind of have an idea, I just need to pick which one I think would work. And so what I'm actually going to do in this video is demonstrate 3 different strategies to show 3 examples of what I hope the students would go through, just to simulate what I hope this would look like in my classroom. And additionally, kind of to show what you could do if you got stuck. So if I used a guess and check first, but I didn't want to use it again because it was difficult, or didn't know how to use it again, then I could go back and think of a different strategy or a different plan to make this happen. So I'm actually going to show an example with guess and check, break it into parts, and work backwards. Alright, so now we have this plan, we have a strategy we can use to attack this problem. We actually need to enact it. We have to carry it out and see what happens. So if I just want to guess and check, okay, guess and check. Well, I'm just going to guess, kind of like I did on that first slide. Well, I'm just going to write down a random equation. I know what an equation looks like. So if I had something like 2x plus 5, what if it was equal to 30? Okay, what if it is equal to 30? Then I'm just going to see what happens. So I know that I want x to equal 10. Excuse me. So what happens when x equals 10 in this problem? So what happens when I have 2 times 10 instead of 2 times x? Well, 2 times 10 is 20 plus 5. This is actually 25, not 30. And so I have to adjust that. I checked to see if my random guess worked. It didn't, so now I need to adjust it from my check. Okay? So now what I actually have is that 20 plus 5 equals 25. And that's true. So I'm going to change my original guess to 2x plus 5 equals 25. Now looking at this, I started it out with x equals 10, so that should be true. I use my variable x, and I have my 2 operations, addition and multiplication. So it's meeting all of those requirements. So I have that first equation. Let's go ahead and try a different method. Alright, so what if we tried breaking it down into parts instead? So what if I knew I wanted to use division and subtraction? Okay, so I'm going to break it down into those different parts. So what can I divide in order to get 10? There are lots of different things, but let's see, 30 divided by 3. That would give me 10. Okay, so that's my division part. So I'm just going to, So I'm going to flip this around. I'm going to use 30 divided by 10 to represent the number 3. All right? And then I want a subtraction part. Well, I could subtract 5, and 3 minus 5 would give me negative 2. So now what I have to do is put this all together. So I have 30 divided by 10 minus 5 equals negative 2. So here's an equation that uses subtraction and division, but it doesn't have a variable in it. So I need to replace my 10 with an x, because I want my problem to end up having the solution of x equals 10. So I'm going to have 30 divided by x minus 5 equals negative 2. And then that equation meets those 3 requirements, or those requirements that I was looking for. All right. The third one, working backwards. So I know that I want x to equal 10. Why not start there? X equals 10, and then work backwards until I have an equation. Okay. So what if, I'm just going to multiply by something. What if I multiply by 7 and see what happens? All right. 7 on both sides. Well, 7 times x is 7x, and 10 times 7 is 70. Okay. Well, that's one part, a multiplication part. So now I need either addition or subtraction. So why not just subtract something? we could subtract 20 and see what happens. We'd have 7x minus 20 equals 50. All right, and looking at this, our answer should be x equals 10 because that's how we started it. We have subtraction, we have multiplication, so we have those two operations, and so this, we have our variable x in there, and so this is fitting those requirements that we need. Okay, so we use those three different strategies to carry out our plan in order to find our three equations. Now, the last step in our four-step problem-solving model, and actually the last requirement for the problem I designed are the same, and that's really look back. In other words, kind of check your solution, prove, show, justify that it works, that it makes sense. And the really nice thing about solving equations is just because of the nature of them, we can either substitute or we can solve the equation to formally check. And so we actually have a really nice way to formally check all of our answers. So I'm going to start with my looking back at my guess and check. So I have my equation I made, 2x plus 5 equals 25. All right, and again, there are two ways I could do this. I know that x should equal 10, so I could substitute that in, or I could solve my equation, and it doesn't really matter which one I do. But what if we substitute? So I'm going to substitute 10 in for x. So instead of 2 times x, we'll have 2 times 10 plus 5 equals 25. Well, 2 times 10 is 20 plus 5. 20 plus 5 is 25. So 25 does in fact equal 25. So we know for a fact that x equals 10 is the solution for this problem. So we know that 2x plus 5 equals 25 works for this. It is a solution to this problem that we were given. Now let's look back at breaking it down into parts. So the equation we made was 30 divided by x minus 5 equals negative 2. Well, again, we could substitute 10 in, or we could solve our equation. So let's substitute 10 in. So we want x to equal 10, and we'll see if that works. So instead of 30 divided by x, we'll have 30 divided by 10. Well, 30 divided by 10 is 3. Minus 5 equals negative 2. 3 minus 5 is, in fact, negative 2. So again, we see that x equals 10 works for this equation. Last one, looking back at our working backwards, we had the equation 7x minus 20 equals 50. Okay, and I'm going to substitute for this one. No, I'm not. I'm sorry. I substituted for the last one. I'm going to solve this equation. So solving it, I'm going to start by adding 20 to both sides. Okay, in which case my 7x stays, but negative 20 plus 20 is just 0. 50 plus 20 is 70. So now I have 7x equals 70. Well, now I can divide by 7. So 7 divided by 7 is just going to leave me with 1x or x, and 70 divided by 7 is just 10. X equals 10, which is exactly what we want. Also notice that when we solve our equation, we can distinctly see that we have those two steps. Here's our first step to add to both sides. Here's our second step to divide on both sides. So it equals 10, and it does meet those other criteria that were set up as well. So we have successfully understood the problem, devised a plan, carried out our plan, and we made sure to look back and check our solutions to make sure they worked. So again, this is an example of a problem I'd like to start doing more with my classes. It's a little bit different than an exercise of just giving the students the problem to solve. It gives them a little bit more of the heavy lifting, while still making sure that they understand how to manipulate equations, how to solve equations and use inverse operations and all of those things. So to extend this, I thought of a couple different ideas. So you could give students a specific number of steps needed for the multi-step. So again, for my equations, the way I set up the problem, it had a minimum of 2 steps that were necessary in order to meet the requirements, but you could say, well, you have to have at least 4 operations in there if you wanted to. Or you could have a variable on both sides of the equation. You can make that a requirement. So you need something like 2x minus 1 equals 4x minus 5. That would add some challenge or a challenge level to it. You could ask them to create problems that involve more than one variable. So have an x and a y aspect to it. Or instead of specifying that what x should equal, you could specify that one side of the equation should equal. So by this I mean you could specify that when you're done, you need to end up with something that equals 52. So we're focusing on this aspect of it instead of focusing on what the variable should be. So those are a couple ideas I had. Thank you for watching.